Hi, my name is Angel. So let's start with 4B, importance of fluids for the circulation of blood, gas movement and gas exchange, which is also a very high yield topic for MCAT. So let's start with fluids physics, right? So in physics, fluids are substances that can flow and do not have a fixed shape, right? So fluids, water does not have a fixed shape, right? It takes the shape of whichever container that you fill it in, right? So they include both liquids and gases. Unlike solids, fluids do form continuously when a force is applied, meaning they cannot resist shear stress without flowing. Fluids take the shape of their container and can easily adapt to any volume or pressure changes. The study of fluids focuses on understanding how they behave under different forces, how they move, and how pressure is transmitted through them. Right? So fluid mechanics is essential in explaining natural phenomena like ocean currents and atmospheric pressure, as well as engineering applications such as hydraulics, aerodynamics, and blood flow in the human body, right? So let's start with density, a very important part, because many other equations are going to be based upon density, okay? So density is defined as the mass per unit volume of a substance. Rho is the is density, right? Rho equals to m by v, so mass by volume. It expresses how compact or concentrated the matter inside a substance is. A high density material has more mass packed into the same space compared to a low density material, right? Density helps predict how substances will behave in fluids such as sinking or floating. For example, when a mosquito lands on water, the mosquito would float, whereas if you throw like a high density something like a really big chunk of stone, chances are it's gonna sink, right? The density equation is one of the simplest but most fundamental relationships in physics and chemistry. Rho equals to mass by volume, right? Density is usually measured in kg by meter cube, right? Mass of the substance, kg or gram. V is volume of the substance, right? All right, so density tells us how much mass is packed into a given volume. High density means particles are tightly packed, like lead, right? While a low density means particles are more spread out, like air, right? So rearranging the equation can be m is equal to mass is equal to rho v to find mass if density and volume are known. V is equal to mass by rho to find volume if mass and density are known, right? So water has a density of about 1 gram per centimeter cube, right? Air at room temp has a density of about 1.2 kilogram per meter cube, right? Gold is extremely dense at 19,300 kilogram per meter cube, okay? So density is itself a very high yield for MCAT, so just pay attention. An IV bag contains 500 milliliter of contrast fluid with a density of 1.20 gram milliliter. What is the mass of the fluid in the bag? So M equals to 120 into 500, right? So we have to find mass, so it's very easy. So all you have to do is volume multiplied by density, right? So the mass of the contrast fluid in the IV bag is 600 gram. Specific gravity. What is specific gravity? The ratio of substance's density to the density of water at a standard temp. Yeah, since it is a ratio, it has no unit, right? So it has no unit. Specific gravity, SG, is a dimensionless quantity that compares the density of a substance to density of a reference material. Usually water at 4 degrees Celsius, where water's density is 1,000 kilogram per meter cube, right? So just remember the density of water, 1,000 kg per meter cube. Chances are you will be provided the information of the density of water. If they ask density of water, you will be provided information of density of water, so you don't have to worry about it, right? Extra information is usually provided on MCAT. Okay, so hold on a second. Okay. So, specific gravity tells us whether an object will float or sink, right? Greater than 1 indicates that substance is denser than water and it will sink, right? While values less than 1 indicate it will float. Mosquito will float, right? Mosquito is not going to sink, right? Whereas if you throw something that's like 1,000 kilogram of a stone, chances are it's going to sink, okay? All right, so Sg is equal to specific gravity, rho substance, density of the material, rho reference, density of the reference, commonly water for liquids, solids, air for gases, okay? Key points, unitless, unlike density, Sg has no units because it's a ratio. Water reference, for most practical uses, water is the reference, right? If Sg is greater than 1, the substance is denser than water, so it sinks, sorry. If Sg is less than 1, the substance is less dense than water and it floats, right? Gasoline has 0.7 and it floats on water, right? It's all right. Iron has 7.9, so it's going to sink, right? Ice, all right, so it's 0.92 and floats, which is what icebergs say above the ocean surface, right? All right, so buoyancy, very important again for MCAT. Buoyancy is the upward force exerted by a fluid that opposes the weight of an object immersed in it, right? It explains why objects float or sink in liquids and gases and is a key concept in physics, engineering, and everyday life. Buoyancy occurs because pressure in a fluid increases with depth. The bottom of an object experiences greater pressure than the top, right? Creating a net upward force. When an object is placed in a fluid, it experiences fluid pressure from all directions. The pressure at the bottom of the object is greater than at the top, creating a net upward force, right? So the pressure at the bottom of the object is greater than at the top, creating a net upward force, right? So if this upward force is greater than the object's weight, it floats. If not, it sinks. Ships float because their shape displaces enough water to generate a buoyant force greater than their weight. Hot air balloons rise because heated air inside is less than the cooler air outside. Ice cubes float in water because ice is less dense than liquid water, right? So as you can see, this particular boat, right? The gravity is pulling the weight of the boat down, whereas the buoyant force of water is pushing the boat up, right? And that's exactly why it is, floating, right? As you can see, it's sailing. Right. So buoyancy is the upward force exerted by a fluid that opposes the weight of an object in the fluid. Fb is equal to rho Vg, right? Rho is the density of the fluid, V is the volume of the fluid displaced by the object, G is the acceleration due to gravity, right? Weight of the object is, pushing it downward, whereas the buoyant force Fb is pushing it upwards. Mass of the object is m, volume of the object is v, density of fluid rho, acceleration due to gravity is g, alright? So weight of the object mg is, as you can see, gravity is pulling it down, whereas the buoyant force is pushing it upwards. Fb, the buoyant force, equals to rho, density vg, v is the volume of the fluid displaced. Alright, so let's use it in a clinical setting. A pathologist places a lung sample into a water bath to assess aeration, right? Very important. The lung displaces 0.8 liter of water. It displaces, right? So that's the volume. You have the volume of displacement. Density of water, rho, is 1.0 gram per milliliter or 1,000 kg per meter cube. What is the buoyant force acting on the lung? So we are looking for FB. So we're looking for rho fluid into gravity, right, into V displaced, right? So V equals to 0.8 liter equals to 0.0008 meter cube. Rho water is 1,000 kilogram, right? And G is 9.8, right? So as you can see, this is, one is liter, and so that's why we had to convert into meter cube. All right, so there you go. Plug in the value, FV is equal to 7.84 newtons, right? So because it's force, it's Newton. So buoyant force on the lung is 7.84, which is enough to make a healthy air-filled lung float. All right, so that's buoyant force, gravity pushing it downward, the buoyant force pushing it upward. FB is equal to rho GV. Okay, so there you go. So Archimedes principle. Archimedes' principle states a buoyant force on an object is equal to the weight of the fluid displaced by the object, right? So what we did right now is explain what the buoyant force is. Now from the FB, we are going to explain Archimedes principle, which is also high yield for MCAT, okay? This principle explains why ships float despite being made of heavy metals and why objects feel lighter under the water, right? So this actually explains why ships float. If the buoyant force is greater than the object's weight, it floats. If it's smaller, then it sinks, right? FB equals to the weight of displaced fluid, all right? Equation of Archimedes, FB is equal to rho GV, where FB is the buoyant force, rho is the fluid density, G is the gravitational acceleration, V is the volume of displaced fluid, all right? Example, imagine a cube of volume 0.05 meter cube submerged in water, rho 1000 kilogram by meter cube. FB equals to 1000 into 9.81 into 0.05 equals to 490.5 newtons. There is a very good chance that 9.81 can be replaced with just 10. And that's what many students do for MCAT, and that's what they want us to do too. So this can very easily be around 500, right? 0.5. Okay. Alright, so key takeaways. Objects float if buoyant force is greater than or equal to object's weight. Objects sink if buoyant force is less than object's weight. Alright, so if the fluid is not displaced enough, that's when it's going to sink. Alright, the principle applies to liquids and gases, so it applies to both. Archimedes' principle states that any object wholly or partially submerged in a fluid experiences an upward force equal to the weight of the fluid displaced by the object, right? So this is gravity pushing it down. This is thrust pushing it upwards. As you can see, the water is displaced, right? So formula FV is equal to P fluid into G into V displaced, right? Again, let's try another example. A solid metal block has a volume of 0.002 meter cube. It is fully submerged in water. What is the buoyant force acting on it? We are asked to search for FB. So FB equals to rho GV, right? So compute FB is equal to 9.6 newtons. Alright, so that was an easy example. What is hydrostatic pressure, right? Hydrostatic pressure is the pressure exerted by a fluid at rest. Right, so it's static, it's hydro, means water, so exerted by fluid at rest, right? It increases with depth due to the weight of the fluid above the point of measurement, right? There is a point of measurement, and I promise you one of the questions will be asked on this, okay? Where you will have to calculate, measurement from the point of the measurement, right? So what is the depth of it, how much weight it is, and you will be asked certain questions like that. The pressure acts equally in all directions, is responsible for phenomena such as pressure felt by the divers underwater and functioning of dams and submarines. Hydrostatic pressure depends only on fluid density, gravity, and depth, not on the shape or size of the container. So the shape or the size doesn't matter. What's important is the fluid density, the gravity, and the depth, right? Definition: pressure in a static fluid caused by fluid's weight. Formula P equals to rho GV. Hydrostatic pressure equals to rho GH, right? Showing dependency on density and depth. So density, gravity, and depth, and that's why we have a little bit of H here. Isotropy acts equally in all directions at a given depth, right? Depth dependency. Pressure increases linearly with the depth, right? So it increases linearly, not horizontally, linearly. Independence of container shape. Only depth matters, not the vessel's geometry. So pH, hydrostatic pressure, is equal to rho GH, okay? Rho is the fluid density. G is the acceleration due to gravity. H is the height of the fluid column, right? A diver is 10 meters below the surface of the freshwater lake inside, right? Find the gauge pressure. Very important. You will be asked something about the gauge pressure. Find the absolute pressure at the depth. Assume atmospheric pressure is 1.01 into 10 raised to 5 pascals, right? So fluid density, rho equals to 1000 kilogram per meter cube, fresh water. Depth is H is equal to 10. Gravity is G is 9.8 meter per second square. Atmospheric pressure, P0, right? 1.01 into 10 raised to 5 pascals. So what is the gauge pressure? Gauge pressure due to water only. Delta P equals to rho GH. All right. So delta P, 1000 into 9.8 into 10, 98,000 Pascal. So the gauge pressure at 10 meter depth would be delta P equals to 98 into 10 raised to 4 Pascal. Right? Step 3 is absolute pressure. Absolute pressure is the surface pressure plus the hydrostatic contribution. So that is absolute, the total pressure, right? So P equals to P0 plus delta P. We just found this delta P, and that's what is applied here. So P equals to 1.99 into 10 raised to 5 pascals, right? So gauge pressure is 10 meter. Absolute gauge pressure at 10 is 9.8 into 10 raised to 4 pascals. And absolute pressure at 10 meter equals to 1.99 in 10 raised to 5 pascals. So let's understand what is the Pascal's law. Pascal's law states that when pressure is applied to a confined fluid, the pressure is transmitted equally and undiminished in all directions throughout the fluid, right? So if you apply the pressure to a confined fluid, a closed fluid, the pressure is transmitted equally, all right? In all directions. This principle forms the foundation of hydraulic systems, right? Transmission of pressure. A pressure applied at one point in a fluid spreads equally in all directions, right? So independence of shape. The container shape doesn't affect how pressure is transmitted. Foundation of hydraulics are used in hydraulic lifts, brakes, and presses. All right, so PA is the unit of pressure, right? So P equals to F by A. F is the force applied by the area over which the force is applied, right? When pressure is applied to a closed fluid system, it is distributed equally to every part of the fluid and the walls of the container, right? So where do we use it? What is the everyday application? Hydraulic car brakes, right? A small force on the brake pedal is transmitted to brake fluid, applying large force on the brake pads, right? Hydraulic lifts used in garages to lift cars with relatively small input force. Hydraulic presses, machines that compress materials using Pascal's principle. Suppose a force of 50 Newton is applied to a piston of area 0.01 meter square, right? So P equals to 50 by 0.01 equals to 5,000 pascals. The pressure is transmitted equally throughout the fluid, so another piston of large area will experience the same pressure but produce a greater force, right? So this pressure is transferred equally throughout the fluid, right? So another piston of a larger area, so let's say if you get another piston of larger area, will experience the same pressure. The pressure is going to be the same, however, it will have a greater force, right? Because as you can see, force by area, so pressure depends on force by area. Okay. All right, Pascal's law explains how small forces can be amplified using fluids, making it backbone of hydraulic systems. What is viscosity? Very important. Viscosity refers to internal friction within a fluid that resists its flow. A fluid with high viscosity like honey flows slowly, while a low viscosity fluid like water flows easily. Viscosity plays an important role in determining how fluids move through pipes, around objects, and inside the human body. All right, so viscosity plays an important role, in explaining how fluids move through pipes and around objects and inside the human body. Definition: viscosity is the thickness of fluid, quantifying how strongly it resists motion. High viscosity fluids, honey, tar, peanut butter, they flow slowly because molecules strongly resist sliding. Right, so viscosity, like I said, it is also refers to an internal friction, right? Low viscosity fluids, water, alcohol, air, they flow easily with little resistance. Fluid friction caused by intermolecular forces when layers of fluid slide past each other, right? Intermolecular forces. All right, so shear stress, all right, dynamic viscosity. So for Newtonian formula, you can use tau equals to mu by du by dy. All right, so shear stress equals to mu, that's dynamic viscosity, and du by dy is the velocity gradient between fluid layers. A layer of oil is trapped between two parallel plates. A bottom plate is fixed. The top plate is pulled to the right with a constant velocity of 0.5 meter per second. The oil layers area is 2 millimeter thick, right? The oil's viscosity is N equals 2.25 pascals by C dot PS, right? Find the shear stress in the oil, right? So compute the velocity gradient dV by dy, 0.5 by 0.002, right? 2 millimeters, 0.002 meter, so 250 second raised to minus 1, right? Apply Newton's viscosity, all right? So shear stress equals to N, all right, dV by dy, that's 62.5 pascal. The shear stress is in the oil is 62.5 pascals, right? So as easy as that, right? So here they use mu for dynamic viscosity. Here they use N. That's the only difference. Poiseuille's flow. Okay, so Poiseuille flow describes a smooth laminar flow of fluid through a long narrow tube under pressure gradient. According to Poiseuille's law, the flow rate increases with the fourth power of the radius of the tube. Very important, incredibly important, yeah, for MCAT. Meaning even small increases in radius greatly increase the flow, right? It also shows that the flow rate is proportional to pressure difference and inversely proportional to viscosity, making it important in biomedical applications such as blood flow through arteries. It is a fundamental principle in fluid dynamics, especially for slow, steady flows where the turbulence does not occur, right? Okay, so volumetric flow rate Q is given by Q is equal to pi r raised to 4 delta P by 8 mu liter, okay? Length of the pipe. So Q equals to volumetric flow rate, meter cube plus by second. R is equals to radius of the pipe, M. Delta P, pressure difference between ends of the pipe, Pascal. Dynamic viscosity of the fluid, PAS. Length of the pipe is M. Laminar flow only applies when Reynolds number RE is less than 2000, right? Strong radius dependency flow rate scales with R raised to 4, meaning small changes in radius drastically affect flow. Higher viscosity equals to lower flow rate, all right? So if due to intermolecular forces, the flow rate is going to reduce, right? Linear with pressure difference, flow increases proportionally with applied pressure gradient. Suppose water flows through a pipe of radius 0.01 meter, length 2 meter with a pressure difference of 500 pascal. Viscosity of water mu equals to 0.001 pascal, right, into seconds. So Q is equal to pi raised to radius, pi into radius raised to 4, right, into 500. 8.8 multiplied by 0.001 into 2, right? So it is approximated 9.8 into 10 raised to minus 5 meter cube per second. So that's like 0.098 liters per second, right? So all you have to do is just apply this particular formula, pi r raised to 4 delta P, right? Delta P is the pressure difference between ends of the pipe, right? Divided by 8 mu dynamic viscosity of the fluid into the length of the pipe, right? So that itself is a formula. Okay. Takeaway: Poiseuille's flow shows how pressure, viscosity, and pipe geometry control fluid transport. It's why tiny arteries can regulate blood flow so effectively, and why engineers must carefully size pipes in the fluid systems. Alright, so what is the continuity equation? A into V equals to constant. The continuity equation expresses the conservation of mass in the fluid flow for an incompressible fluid. Alright, we saw compressed fluid. Now we're going to talk about incompressible fluid. The product of the cross-sectional area of the pipe A and the velocity of the fluid V remains constant. Right? This means that if a pipe narrows, the fluid must speed up. And if the pipe widens, the fluid slows down, right? The continuity equation applies to water flow in pipes, blood flow in vessels, even air movement in ducts. Formula: A1V1 equals to A2V2 equals to constant. A is cross-sectional area of the pipe, m raised to 2. V equals to fluid velocity at the section meter by second. Constant represents the volumetric flow rate Q, which is conserved, right? So Q equals to A into V, right? Okay. Key concept: conservation of mass. Fluid entering a pipe must equal fluid leaving it. A1V1 equals to A2V2, right? There you go. Inverse relation: if the pipe narrows, the smaller a velocity increases. Applies to incompressible fluids. Continuity equation applies to incompressible fluids, right? Works best when fluid density is constant, right? The rho is constant. Basis for Bernoulli's principle, very important, right? Continuity equation is often paired with energy conservation, right? All right, so water flows through a pipe at section 1, A1 equals to 0.05 meter square, V1 equals to 2 meter per second. At section 2, A2 equals to 0.02 meter square, right? Using continuity, we have to find the V2, right? The volume 2. A1 V1 equals to A2 V2. 0.05 into 2 equals to 0.02 into V2. V2 equals to 5 meter per second. All right, so velocity increases to 5 meter per second in the narrower section, right? So if it's narrow, velocity is going to increase. All right, so what are the real world application? The garden hose and nozzle, right? Narrow nozzle increases water speed, blood flow, arteries narrowing, stenosis cause faster blood velocity. Aircraft engines, air accelerates through narrowing ducts. Hydraulic systems ensures mass conservation in fluid circuits. Continuity equation is a cornerstone of fluid dynamics, showing how geometry controls velocity. Okay. Turbulence. What is turbulence at high velocities? Turbulence refers to irregular, chaotic motion of a fluid that occurs at high velocities or when the flow is obstructed. Unlike smooth laminar flow, turbulent flow involves swirling eddies, rapid changes in velocity, and increased energy loss due to friction. All right. Turbulence affects the efficiency of fluid systems, increases drag on moving objects, and plays a major role in weather patterns, aircraft design, and pipeline engineering. Turbulence is a complex, chaotic fluid motion that occurs when the velocity of fluid becomes high enough that orderly laminar flow breaks down. Instead of smooth layers, the fluid develops eddies, vortices, and random fluctuations in velocity and pressure. All right, the onset of turbulence is often predicted using the Reynolds number RE, right? PVD by mu, right? So rho VD. Rho is fluid density, V is flow velocity, D is characteristic length, the pipe diameter. Mu is dynamic viscosity. So the laminar flow Reynolds number is less than 2000. Transitional flow 2000 is less than Reynolds number less than 4000, right? Turbulent flow RE is greater than 4000, right? All right, at high velocities, RE increases, making turbulence inevitable, right? So high velocities. All right, so a real world example would be airflow over airplane wings. At high speeds, turbulence increases drag and fuel consumption. Blood flow rate in arteries, high velocity due to narrowing can cause turbulent flow, linked to medical conditions, right? High velocity due to narrowing can cause turbulent flow. All right. River rapids. Fast moving water becomes turbulent, right? We've seen that, forming whirlpools and chaotic currents. Industrial pipelines. High fluid velocity causes turbulence, affecting efficiency and water and wear, all right? So you've seen that. What is surface tension? What is surface tension? Surface tension is tendency of liquid's surface to behave like a stretched elastic membrane, right? It arises from cohesive forces between molecules. Molecules at the surface experience a net inward pull, which reduces the surface area and causes droplets to form spherical shapes. Surface tension is responsible for phenomena such as insects walking on water, water droplets forming beads, and capillary action in thin tubes, right? So surface tension, I usually just say T equals to F L. F equals to force acting along the surface, that's Newton. Length, L, is the length over which the force acts. It can also be expressed as energy per unit area, right? So you can express it as work by area. A thin wire frame holds a soap film. One side of the frame is a movable wire of length 0.10 meter. The surface tension of the soap solution is T equals to 0.030 Newton per meter. The film has two surfaces, front and back. Find the force needed to keep the wire in equilibrium, right? Use the surface tension equation, right? So T equals to F by L effective, right? So 0.030 Newton, right, into 0.20 equals to 0.006 Newton, right? The force we needed to hold the wire in equilibrium is 0.006, all right? Okay. So the reason why they said two and not just one is because the film has two surfaces, front and back, right? Bernoullis equation, very high yields. Bernoullis equation states that in a steady ideal fluid flow, the sum of pressure energy, kinetic energy, and potential energy remains constant. As fluid velocity increases, the pressure decreases and vice versa, right? This relationship explains many real-world effects, right, including the lift on airplane wings, the narrower of the river flow under bridges, and the narrowing of river flow under bridges, and changes in pressure within blood vessels, right? So what is the equation? P plus half rho v squared plus pgh equals to constant, right? So P is pressure energy per unit volume, right? So that's Pascal. Half rho v squared kinetic energy per unit volume, fluid velocity, right? Rho gh, potential energy per unit volume. Rho equals to fluid density, right? V is fluid velocity. Elevation above reference point, right? Gravitational acceleration 9.81. For MCAT, you can take 10. Energy conservation, the sum of pressure, kinetic, and potential energy remains constant along a streamline. Inverse relationship, if velocity increases, pressure decreases, basis of lift in airplane wings, right? So velocity increases when the plane is flying. That's exactly how it takes up. Why? Because the speed increases. All right, the height effect. Fluids at higher elevation have greater potential energy. Fluids at higher elevation. Ideal assumption works best for incompressible, non-viscous fluid in steady flow, right? All right, so water flows through a horizontal pipe at section 1. Velocity is 2 meters per second. Pressure equals to 200 kilopascals, right? So at section 2, velocity 4 meters per second. What's changing is the velocity, right? So P1 plus half rho v squared 1 equals to P2 plus half rho v squared 2, right? So rho here has 1,000, kilogram per meter cube for water, density for water. So and here 200,000 plus half 1,000 2 raised to 2, P2 half into 1,000 4 raised to 2. That's the only difference. So the pressure drops to 194 kilopascals, right? Kilo is 3 zeros. So kilopascal when velocity doubles. Real world application. The real world application here would be airplane wings. Faster airflow above the wing reduces pressure, creating a lift, right? Venturi meters, very important, measure fluid flow rate using pressure differences. Chimneys, draft is explained by bernoullisprinciple, right? Spray bottles, pressure differences draw liquid upward and atomize it, right? So spray bottles, pressure differences draw liquid upward, and you can actually spray it at a wider area. Why do you think that's happening? Because due to pressure difference, right? All right, Bernoullis equation shows how pressure, velocity, and height are interconnected in a fluid flow, right? It explains why fluids speed up in a narrow passage and why pressure drops in fast-moving streams, right? All right, so there is an inverse relationship between velocity and pressure. That's what it's explaining. Venturi effect, very important. Venturi effect is the phenomenon where fluid pressure decreases as fluid velocity increases when passing through a constricted section of a pipe, right? The Venturi effect is used in devices like carburetors, respirators, and medical oxygen masks to mix or regulate fluid flow. Relation to Bernoullis principle. Bernoullis equation explains that the sum of pressure, energy, kinetic energy, and potential remains constant, so higher velocity means lower pressure. Conservation of mass, the same amount of fluid must pass through the both wide and narrow section. All right. So pressure drop, the static pressure is constriction is lower than the wider section. Velocity increase, fluid speed rises in the narrow section compared to the wider one, right? So fluid speed is rising in the narrow section, right? Narrower, right? The area is reverse, right? Inversely proportional, right? Fluid speed rises in the narrow section compared to the wider one. Venturi effect equation. P1 plus half rho v squared 1 equals to P2 plus half rho v squared 2. All right. Continuity equation. A1 V1 equals to A2 V2 cross-sectional areas. Combine Venturi equation pressure velocity relationship, right? P1 minus P2 equals to half rho V2 square minus V1 square, right? So using continuity, V2, all right, equals to V1 A1 by A2, right? So the flow rate through a Venturi meter, Q equals to A2, right, square root of 2, P1 minus P2 divided by rho 1 minus A2 by A1 square, all right? So let's say what a pitot tube measures the speed of moving fluid using pressure differences. It has one opening facing the flow to measure stagnation pressure and another to measure static pressure. The difference between these pressures determines fluid velocity. The pitot tubes are widely used in aircraft to measure airspeed and in engineering applications requiring accurate flow measurement. All right, so the principle of pure Bernoulli. The front-facing opening brings the moving fluid to rest. This gives stagnation pressure, right? A separate static port measures the ambient static pressure. The difference between the stagnation and the static pressure is the dynamic pressure, which relates directly to velocity, right? P total is equal to P static plus half rho V square. Right, so velocity of V equals to square root of 2 P total minus P static divided by rho, divided by the density. All right, so this is very important, gas phases. Gas phase is a state of matter. Particles are far apart and move freely in all directions. All right, so gases do not have a fixed shape or volume. Instead, they expand to fill any container because the particles are widely spaced. Gases are highly compressible and respond strongly to changes in temp and pressure. Understanding gas behavior is important in both science and industry because gases follow predictable laws that help explain how they expand, compress, and react. All right. In the gas phase, particles are far apart, move freely, and possess high kinetic energy. All right, this leads to several hallmark properties: low density compared to solids and liquid, high compressibility because particles have large spaces between them, no fixed shape or volume, gases expand to fill any container, constant random linear motion of particles. This characteristics makes gas uniquely predictable using gas laws like Boyle's, Charles, and ideal gas. All right, absolute temp, Kelvin scale. Absolute temp is measured on the Kelvin scale, right, which starts at absolute 0, the lowest possible temp where particle movement is almost 0. Kelvin scale is used in gas calculation because gas behavior depends directly on temp measured from absolute baseline. So K equals to Celsius plus 273.15. This ensures that temp values are always positive when using gas laws. Absolute temp is temp measured on a scale whose 0 point is absolute 0. The lowest possible temp where molecular motion reaches its minimum. The Kelvin K is the SI base unit of thermodynamic temp. It's an absolute scale that begins at 0 K, which corresponds to absolute 0. Starts at absolute 0, so 0 K is theatrical point where particles have minimal Ke. No negative values. Unlike Celsius or Fahrenheit, Kelvin values are always positive because they measure energy directly. All right, so a change of 1K equals a change of degrees Celsius. The scales differ only in their starting points. So defined by using Boltzmann constant. Modern definition fixes the Boltzmann constant at 1.380649 into 10 raised to minus 23 JK, right? All right, so joules Kelvin. All right, so TK, example, convert 25 to Kelvin. TK equals to TC, all right, degrees Celsius plus 273.15. Right, so just add it and you'll have 298.15 Kelvin, right? To convert 310 Kelvin to Celsius, all you have to do is subtract 273.15 from the Kelvin, okay? So that would be 36.85 degrees Celsius. Pressure and a simple mercury barometer. Pressure is the force exerted per unit area. Atmospheric pressure is the weight of the air above a given surface. Pressure in a gas is created by the constant collision of gas molecules with the walls of pressure in a gas is created by the constant collision of gas molecules with the walls of their container. The more frequent and forceful the collisions, the higher the pressure. A simple mercury barometer measures atmospheric pressure using a column of mercury in a glass tube. Atmospheric pressure pushes down on the mercury in the reservoir. And this supports a column of mercury inside the tube. Higher air pressure equals to taller mercury column. Lower air pressure equals to shorter mercury column, right? This balance between the weight of the mercury column and the pressure of the atmosphere to the core principle of the barometer. The height of the mercury column represents the pressure with standard atmospheric pressure equal to 760 millimeter Hg. Right? This device helps scientists understand weather patterns and how gases behave under different conditions. Alright, so molar volume at STP, standard temp and pressure, 0 degrees Celsius and 1 atm. Right, 1 mole of an ideal gas occupies 22.4 liters, is known as a molar volume of gas at STP. It is useful because it allows quick and easy conversions between moles and volume when studying gas reactions, right? What is an ideal gas? An ideal gas is a theoretical model of a gas whose particles do not attract or repel each other and take up no volume, right? So although no real gas perfectly behaves this way, many gases act like ideal gases under normal conditions. The ideal gas model makes it easier to understand and predict how gases respond to the changes in pressure, temp, and volume. Ideal gas PV equals to nRT. The ideal gas law combines several gas relationships into one equation. PV equals to nRT. It shows that pressure, volume, temp, and number of moles of gas are all related. If one of these factors changes, at least one of the others must also change. The equation is widely used to solve problems involving gases in chemistry, physics, and engineering. The ideal gas law combines several simpler gas laws into a single relationship. It states that PV equals to nRT. P equals to pressure of the gas, V equals to volume, number of moles, ideal gas constant, temp in Kelvin. Boyle's law states that for a fixed amount of gas at constant temp, the pressure is inversely proportional to the volume. If the volume decreases, the pressure increases because the gas particles collide more often with the walls of the container. This law explains everyday examples like how syringe works or why squeezing a balloon increases its pressure. PV equals to K, right? If volume decreases, the pressure is going to increase. The volume increases, the pressure is going to decrease, right? The product PV stays constant as long as temp doesn't change. A gas has a volume of 4.0, okay, at a liter at a pressure of 1.2 atm. If the pressure is increased to 2.0 atm, what is the new volume, right? So P1 equals to 1.2 atm, V1 equals to 4.0 L, and P2 equals to 2.0. We have to find V2. So all you have to do is just plug it, and we'll find that it's 2.4 liters, okay? So Boyle's law is P1 V1 equals to P2 V2, right? So what is Charles' law? Charles' law Vt equals to constant, right? V by T equals to constant. Charles' law states that for a fixed amount of gas at a constant pressure, the volume is directly proportional to its absolute temp, right? So when gas particles gain heat, they move faster and push outward, causing volume to expand. This law explains why a heated balloon expands and why the volume of gas increases when they are warmed, right? So V by T equals to K, right? So if temp increases, the volume increases. If temp decreases, the volume also decreases, right? The ratio V by T stays constant as long as the pressure doesn't change, all right? So this law explains why a heated balloon expands and why the volume of gas increases when they are warmed, right? So what it states, a fixed amount of gas at a constant pressure, the volume is directly proportional to absolute temp, provided it's a fixed amount of gas and the pressure is kept constant. All right, so Avogadro's law, V by N equals to constant, very important. Avogadro's law states that at constant temp and pressure, the volume of gas is directly related to the number of moles of gas present, right? This means that equal volumes of gases under the same conditions contain the same number of molecules, right? So this principle is useful in chemical calculation and helps in understanding gas mixtures and reaction. If moles increase, the volume increases. If moles decrease, the volume decreases. The ratio of V by N stays constant as long as temp and pressure don't change, right? So if volume increases, if moles increase, the volume are going to increase. If moles decreases, the volume is going to decrease, all right? Or V by N equals to K, right? And K stays constant, right? A gas occupies 8.0 liter when it contains 0.50 moles. If the amount of gas is increased to 0.80 mole at the same temp and pressure, what is the new volume? So here we have to find the volume. V1 by N1 equals to V2 by N2, right? Substitute values and we'll find V2, right? So we'll find the second volume, right? So like it says, if mole increases, the volume is going to increase, and the mole decrease, the volume is going to decrease, right? All right, so kinetic molecular theory of gases. KMT describes a gas as a huge number of tiny particles in constant random motion whose collisions with container walls create pressure. It provides the molecular basis for Boyleslaw, charleslaw, Avogadro's law, and ideal gas law. Right? Ideal gas is PV equals to nRT. All right, so core assumption, the standard 5-point model. Gases consist of extremely small particles, atoms, or molecules that are far apart relative to the size. Particles move in continuous random straight line motion until they collide with each other or the container walls. Collisions are perfectly elastic, meaning no net loss of kinetic energy during collisions. There are no intermolecular forces between gas particles. They neither attract nor repel each other. Average kinetic energy is directly proportional to temp in Kelvin. Boltzmann's constant Kp. Boltzmann's constant is a fundamental physical constant that links the average kinetic energy of gas particles to the temp of the gas. Its value is Kp equals to 1.38 into 10 raised to minus 23 joules per Kelvin. It shows that temp is a direct measure of microscopic energy of particles. In the kinetic theory, the average kinetic energy of gas molecule is given by Ke equals to 3 by 2 Kp. T, okay? This constant is essential in statistical mechanics, thermodynamics, and understanding molecular behavior in gases. Deviation of real gas behavior. This is not very high yield. Real gases do not always follow ideal gas law perfectly at high pressures and low temps. This is because actual gas molecules have volume and experience intermolecular forces, which the ideal gas model ignores. As a result, real gas behavior deviates from predictions of ideal gas equation PV equals to nRT in certain conditions, right? Real gases deviate from ideal behavior mainly due to two factors. What are the conditions? Intermolecular forces. In real gases, particles attract each other, and when they are close, at low temp, these attractions slow the particles down and lower pressure compared to ideal predictions, right? Finite molecular volume. Gas molecules have actual size, so they cannot be compressed endlessly. At high pressures, the available volume becomes smaller than the ideal gas law assumes because molecules occupy space between themselves. This makes the measured volume larger than the ideal prediction, right? So thus, the real gases behave more ideally at high temp and low pressure and deviate strongly at low temp and high pressure. The quantitative explanation, van der Waals equation, P plus A, all right, that shows the intermolecular attraction by V2, V minus B equals to RT, right? So this equation provides a more description of real gas behavior, especially near liquefaction and at extreme conditions, right? What is partial pressure, right? So partial pressure is the pressure that a single gas in a mixture would exert if it occupied the entire container by itself at the same temperature. So right, it's the individual contribution of each gases to the total pressure. All right, so atmospheric oxygen's partial pressure is only a fraction of total atmospheric pressure. Respiratory physiology, gas diffusion in the lungs is driven by difference in partial pressure, not concentration. Anesthesia, gas mixtures are calibrated using partial pressures, right? Diving, partial pressures determine safe breathing gas mixtures, right? So Dalton's law tells us P total equals to P1 plus P2, right? So each PI is a partial pressure. Mole fraction connection. Partial pressure can also be expressed using mole fraction. PI equals to XI P total. This is incredibly useful for gas mixtures, respiration physiology, and vapor pressure problems, right? Mole fraction. Mole fraction is the ratio of the moles of one of the component to the total moles in the mixture. It is dimensionless and often written as XI or XI, okay? Xi equals to Ni by N total, Ni equals to moles of component I, N total moles of all components, right? Dalton's law of partial pressure. Dalton's law states that in a mixture of non-reacting gases, the total pressure is the sum of the partial pressure of each individual gas. Mathematically, P total is equal to P1 plus P2, all right, plus, if there are different gases, they may have different pressures, plus Pn, right? So numerous gases. Each gas behaves as if it is alone occupied the container. Mole fraction from Dalton's law can also be expressed using mole fraction Pi is equal to Xi P total, where Xi is the mole fraction of gas I, right? So Dalton's law explains how atmospheric pressure arises from nitrogen, oxygen, CO2, right? How to calculate pressure in gas collection experiments over water, how to calculate pressure in gas collection, right? So each would have its own pressure. How anesthetic gas mixtures are formulated, like we just saw that they're calibrated, each of them are calibrated, right? How gas exchange works in physiology, especially when it comes to partial pressure that drives diffusion, all right? So there you go. This was importance of fluid for circulation of blood, gas movement, and gas exchange. All right. This was based off AAMC. If you really like this video, please like, subscribe, and comment. All right. Thank you.